Okay, so hi everybody. So yeah, if you have questions, you can either raise your hand or I mean that's best. Then then you can just say the question. You can also write in the chat, but it's actually better if you just ask. So okay, so it's lecture 20. Oh yeah, so the stuff in this lecture is not going to be on the midterm. Half the lecture is going to be just wrapping up chapter 6. And the other half is going to be sort of a mini review session. And as you might have seen on B courses, the midterm is now untimed open book exam for 24 hours. And you'll receive more details about that later. So I want to do 3 things in this lecture. The one is I want to finish talking about least squares and talk a little bit more about orthogonal projections, which are a really important class of linear transformations, really one of my favorite, which come up a lot. Second, I want to tell you about something that it's not really that emphasized in the book, but in some other textbooks, it's actually called the fundamental theorem of linear algebra. So it's a really important. Oh, thanks. Yeah, somebody. Great. Yeah. Well, I'm glad. I'm glad. Yeah, there's no need to add stress to an already stressful situation. And then finally, I'm going to do a mini review session. Okay. So what was least squares? So last time we introduced this notion of a least squares solution to a linear system. And this was the following problem: that you're given a matrix A, maybe an m by n matrix, and some vector B in Rm. The question is to find some x hat that's as close as possible to solving ax equals b. And what that means is you want to find one that minimizing, I suppose, this square norm error. That's why it's called least squares. Okay. And so what in the last lecture we so the picture that goes with this is something like this. There's the column space of A, and then there's maybe Rn, which is being mapped into the column space of A by A. And this column space of A is contained in Rm. It's a subspace, and you're given some vector B, which may not be in the column space. And what you're asking to find is you're asking to find some x hat that's actually sitting back here. And this should have the property that it gets mapped to some vector that will, by definition, be in the column space. Let's call that B hat. And that B hat better be the closest vector to B in Rm. Okay, so that's a picture of least squares. And we came up with 2 ways to solve this problem. So solution 1 was sort of what's suggested by this picture, 2-step solution. First step is to find the projection, B hat, which is the projection onto the column space of A of B. And then maybe a second step. So I'll write to 2. The second step was then solve Ax hat equals B hat. So that's a 2-step solution. But then what we actually noticed is that there's a more clever solution that only has 1 step. It's based on this fact that the minimizing B hat has the property that B minus B hat is orthogonal to the column space. And using that, we actually just found a single linear system whose solution will find an x hat. And the second solution is just solve the normal equations. And that just means you solve the related system A transpose AX hat equals A transpose B. And just to make sure we understand this, what are the dimensions of this matrix A transpose A?
N by N.
N by N, yeah, because A transpose is N by M. So N by M times N by N is N by N. And this is now a vector actually in Rn, right? A transpose B. Okay, just to illustrate this, let me do a concrete example. So the example is I have a matrix A, which is the matrix minus 1, 2, 2, minus 3, minus 1, 3. And I have some vector B, which in this case will be the vector 4, 1, 2. And I want to find some x hat, which will be in R2, minimizing this this squared norm error. So AX equals B is actually not consistent for this A. And so what are the normal equations? Well, okay, what's A transpose A? So that's a matrix. So A transpose is the matrix minus 1, 2, minus 1, 2, minus 3, 3. A is just the same as it was. And so when you multiply these, just in the usual way, what you get is a 2 by 2 matrix whose entries are 6, minus 11, minus 11, and 22. Okay. So by the way, this matrix has this funny property that the two off-diagonal entries are actually equal. Do you think that's a coincidence? So can anybody explain why this has this property that the off-diagonal entries are equal?
Yes. Yes, because the diagonal, because they're basically dot products of the two same vectors.
Great, that's a good explanation. So this matrix, by the way, has a property that if you look at the ij entry, well, it's just going to be the dot product of the ith column of A with the jth column of A, right? Because the ith row of A transpose is the ith column of A. And so that's going to be equal to aj dot ai, which is going to be equal to the ji entry. Okay, so this always happens. This is not an accident or anything like that. And another way to see it algebraically is just that, well, A transpose A transpose is A transpose times A transpose transpose, which is just A transpose A, which is the same thing. So the matrix is equal to its transpose. So here are two ways to see this. It's called a symmetric matrix. Anyway, that's A transpose A. Then you calculate A transpose B, which is in this case minus 1, 2, minus 1, 2, plus 3, 3 times the vector B. And if you do that, you get the vector 4 minus 11. And so now the normal equations are asking you to solve this linear system. 6 minus 11, minus 11, 22, 4 minus 11. And if you row reduce this, you get 3, 2. And so what this is telling you is that x hat equals 3, 2 is a least square solution. Okay. So that's what I mean by the normal equations. And in particular, the normal equations are always consistent. . The reason is the least squares solution always exists, right? It's a minimization problem. There's always some x hat that's, that minimizes this quantity. And such an x hat always satisfies the normal equations. So the normal equations always have a solution. So this is, it's a special type of linear system that's always consistent. But now I can ask one more question. When is x hat unique? Right? So x hat always exists, but when is it unique? And this has an interesting answer. You can actually get two different answers to this, depending on whether or not you look at solution 1 or solution 2. Right? So the first answer, looking at solution 1, is, well, x hat is unique if and only if ax hat equals b hat has a unique solution. Right? Because b hat is unique. B hat is just the projection of b onto the column space. There's no non-uniqueness there. And this is true, if and only if A has linearly independent columns, which is another way of saying that the rank of A is equal to n, because there are n columns. Right? So that's one exact condition for when when x hat is unique. But you can actually get a second answer by looking at the normal equations, right? Because there are two different ways of computing x hat. So it's unique if and only if the normal equations have a unique solution, A transpose. And now that's a different linear system. And well, that has a unique solution when A transpose A is invertible, right? A transpose A is a square matrix. So it's true if and only if A transpose A is invertible. Okay. And so, so this actually, so since these are two different statements equivalent to the same condition, namely uniqueness of x hat, we actually derived something kind of interesting, which is that these two conditions are also equivalent, right? Because they're both equivalent to x hat being unique. So actually, we derived a pretty interesting fact, which is that A has rank equal to the number of columns if and only if A transpose A is invertible. And there's actually an instance of a more general fact, which I won't derive in class, but you can derive it using similar reasoning, which is that rank of A transpose A is equal to rank of A in general. Okay, this is a not obvious fact, but you can derive it using this reasoning about least squares. Another consequence of this is that the second condition actually gives you a formula for the least square solution when A is invertible. So I'll just write that on the next slide, or maybe I'll write it here. So if A transpose A is invertible, or maybe I'll write if there's a unique solution. Then, well, then A transpose A is invertible. So that means this system here, I can just write a formula for x hat by multiplying by the inverse of A transpose A. So what you get is that then x hat must be equal to A transpose A inverse A transpose B. So you get a formula for the least square solution when the solution is unique. Okay, so that's sort of our study of the uniqueness properties of the least squares problem. The solution is unique exactly when A has, full rank. And if it is, then it's given by this formula related to the inverse of A transpose A. And this is sort of one byproduct of this reasoning, which, I mean, well, you can think about offline. Okay, so any questions about this?
So what is the connection between the linear independent columns and invertibility in this case?
Well, A has linearly independent columns if and only if A transpose A is invertible. That's the connection. They're equivalent. Why?
Okay.
Because they're both equivalent to X hat, the uniqueness of X hat. So suppose I'm given an A and a B and I ask to find the least square solution X hat. I can ask, when is X hat unique? And I derive two different answers to that, right? But actually, since they're both equivalent to X hat being unique, they're equivalent to each other. Does that make sense?
Yes, thank you.
Yep. Yes, please. You can ask. You raised your hand.
So does that also mean that the product of A and A transpose will give linearly independent columns?
Does it mean A transpose A has linearly independent columns? Yes.
Okay.
Because remember, A transpose is a square matrix. So being invertible is the same as having linearly independent columns.
Yeah. Okay.
Yep. Any other?
So I
Yeah.
want to ask why it's kind of like A transpose and A is invertible. Like,
Why is
there
A
any
transpose A
proof?
invertible?
Yeah. Is there any
Oh.
proofs?
Oh yeah. So the proof is going back to before the first midterm, right? When does a linear system have a unique solution? Well, it doesn't actually depend on the right-hand side, right? It only depends on the matrix of coefficients, which in this case is A transpose A. Right? Uniqueness of a solution means pivot in every column. But if it's a square matrix, so it's a square matrix, right? A transpose A is square. So that's equivalent to being invertible. Does that answer the question?
Oh, so that means that it has rank of n, and also because AT times A is a square matrix.
Exactly.
So
I'm using that it's a square
so it
matrix.
pivot every column.
I'm using that it's square. Okay, so maybe I should put that this is like homework or something, so I'm not going to prove it right now. Any other question? Okay. So that's about least squares. So now I want to say a little bit more about orthogonal projections and some terminology surrounding them that's can be a little bit confusing. Okay, so remember that if you have a subspace of Rn, let's say, then then there's this linear transformation, the projection onto W from Rn to Rn, which is called the orthogonal projection. And you know, okay, I won't rehash everything about it, but one thing I want to derive is what does the matrix of this orthogonal, what does the standard matrix look like? Right, so this is some linear transformation, so it should have a standard matrix, which would be a square matrix. What does it look like? Well, let's derive this. So we're going to do something a little funny. We're going to just pick some arbitrary orthonormal basis for W. Okay, we know that such a basis exists because we proved every subspace has an orthonormal basis. That follows from Gram-Schmidt, right? Okay, somebody's asking to go to the last slide. Is there a specific question? Or maybe this one? Any question about this? Jose Garcia, you asked to go back to the slide. Any question? Okay, sure. Okay. As I said, so the question was, how do we find the standard matrix? Well, I mean, there's a usual formula for doing this, right? Which is to just apply the transformation to the standard basis vectors. But I'm going to do it differently this time. So suppose U1 through UP is any orthonormal basis of W. And what's the formula for the projection? So for any vector x in Rn, the projection onto W of x has this formula, right? It's x dot U1 times U1 plus x dot U2 times U2 all the way up to x dot UP times UP. We have this formula, we derived it earlier, right? But now I'm going to just rewrite this in matrix notation and see that it actually gives me a matrix that implements this projection, and therefore that has to be the standard matrix, right? Because the matrix is unique. So, so what is this? Well, this is a linear combination of U1 through UP, right? So let's now make a new matrix. Let's call it capital U, and its columns are going to be these orthonormal bases. U1 orthonormal. That's why there are no denominators. Okay, so I'm going to make this matrix U, which is going to be an n by p matrix, right? So now this formula is just taking a linear combination of the columns of U. So I can write it as a matrix vector product. So I can write this as U1 up through UP times the coefficients in the linear combination, which are just dot products, which I'm going to suggestively write as transposes. Okay, I'm not sure what's going on here. Right? That's just because dot products can be written as transposes. Okay. Well, now I'm going to use another interpretation of matrix vector multiplication, a different one, the high school interpretation, which is when you multiply a matrix by a vector, you're actually just taking dot products with that vector, right? So now I can write this as this matrix whose columns are the UIs. Now times another matrix whose rows are the UI transposes. Times the vector, okay, x. I mean, let me just write it as x. I don't need to write the coordinates of x. Okay, but that's it. That's the matrix, right? That's UU transpose times x. So the formula actually tells me what the standard matrix is. It must be this, right? Because this is true for every x in Rn. So the conclusion is that the standard matrix of the projection, so this means standard matrix, is actually equal to UU transpose. And there's a funny thing about this, which is even though I used U to find this matrix, this matrix UU transpose that I get actually doesn't depend on the choice of U. Right? U does depend on the choice of the basis U1 through UP, but UU transpose doesn't. It only depends on the subspace, right? The orthogonal projection is well defined without choosing a basis. So this is an important class of matrix, which is called a projection matrix. And projection matrix means a standard matrix of an orthogonal projection. Okay. So So here are some, okay, so by the way, this is an n by n matrix. And here's how this matrix is related to the subspace W. So the rank of this projection matrix. So what's the rank going to be? It's the dimension of the column space of this matrix. So what's the dimension of the column space of the projection onto W? Yeah, it's the dimension of W. Right? And similar, I mean, okay, nullity is just the dimension of W perp. And actually, all the eigenvalues are 0 or 1. You can check. So you can check this as, I mean, I said this last time. As eigenvalues are 1 with multiplicity dimension of W, geometric multiplicity, and 0 with multiplicity dimension of W. Okay, and another way that this comes up a lot that people often describe projection matrices is if P is a projection matrix, then P squared equals P. Nullity means dimension of null space. Okay. So those are called projection matrices. Somewhat confusingly, there's another class of matrices that are called orthogonal matrices. Right? And these are not the same thing as orthogonal projections. So a matrix U, a square matrix, is called orthogonal if it has orthonormal columns. Okay, so it has to be square. And a way to see this is, so this is the same thing as saying U transpose U is equal to the identity. Why? Well, because same reasoning as in the normal equation slide, the ij entry of this is just going to be the dot product between the ith and jth columns of U. Okay, and explain this. Yes. So why is U transpose U ij equal to ui dot uj? Well, that just follows from the type of reasoning that I did over here. I mean, okay, let's just write it out, right? If you literally write it out, you have U1 transpose. Is this the statement you're asking about? The previous slide? This slide? Yes. Oh, this, yeah. So a matrix is called orthogonal if it has orthonormal columns and is square. That's the definition. Okay. Is that okay? I mean, the reason I'm telling you, oh, what I said about eigenvalues, yeah. Well, so the reason for this is that if you have any vector in W, then the projection of W, the projection onto W of X is just X, right? So that means that's an eigenvector. It didn't change the direction, it just multiplied by 1. Does that make sense? And this is because if you have any vector in W perp, the projection onto W of that vector is 0. Okay, so before I go back to the slide, does this answer the question about eigenvalues? Okay.
Can I ask a question?
Yes, please.
Okay, so can you go back to the previous slide?
Yeah.
The previous one.
This one? This one?
No, the previous.
Yeah.
The previous of this one. Okay,
This one?
so the next one.
This one?
The next one. So well, the UTU.
Yeah.
Then
Oh, UTU. So this one.
Yes. So basically I'm asking like, how did you come up with like so how did you come up like, so basically the U.
So you.
Matrices of V1tx to VPTX, but according to the matrix multiplication algorithm, you should like row and column. You should times row and columns.
Right.
But
Right.
all of the all of the U1 and UPs are all like columns in the first place.
No. So I've defined U to be orthogonal if it has orthonormal columns.
Oh no, I mean the orthogonal projections.
Yeah. So this is different. This is not the same as what's written on the next slide. This is UU transpose. It's not the same. The first matrix actually has columns and the second one has rows.
Mm-hmm.
So this is not what you're used to doing in high school, right? You're not multiplying the rows of the first matrix by the columns of the second one.
Mm-hmm.
The first matrix has columns and the second has rows.
So like, what is like the U1 to UP represents?
That's the orthonormal basis I chose for the subspace W.
So because that is X times U1 and U1. Okay, I got it.
Yep.
Oh,
so I think the confusion is that what's written on this slide is really not the same as what's written over here. What's written over here is the opposite picture, right?
Mm-hmm.
Where the rows come in the first matrix. Right?
Yes.
So this is not the same thing. This is different from the formula for a projection matrix.
Mm-hmm, mm-hmm.
Okay, and that's kind of why I'm telling you this, because it's very easy to be confused. There's something called an orthogonal projection. Its matrix is called a projection matrix. And that's a matrix that looks like UU transpose. Then there's something else called an orthogonal matrix, which is a square matrix. So it's a U transpose U equals I. Now, I should say that this actually implies that U transpose equals U inverse, right?
Mm-hmm.
But then that implies that UU transpose also equals I. For this square case. Okay? So for general matrix, U transpose U and UU transpose are not the same thing. If you have any matrix with orthonormal columns, then U transpose U equals I. But UU transpose in general is a projection matrix. It cannot be I. Okay? So that's somehow the distinction I want to make here, that for a projection matrix, this UU transpose is not the same as U transpose U, which is equal to I, which is equal to a P by P identity.
Okay, thank you.
So that's what a orthogonal matrix is. And what's the meaning of an orthogonal matrix? Let me just say.
Hi, Professor. Can you quickly,
Mm-hmm.
sorry, can you go back to the previous slide?
Yeah.
So for the eigenvalues, I have trouble understanding the first part. So like after your second explanation, I understand that part, but like one geometric multiplicity.
Oh yeah. So what I mean is the eigenvalue is 1, And every eigenvalue has a geometric multiplicity, right? Namely, the dimension of the corresponding eigenspace.
Mhm.
So what I really mean is the geometric multiplicity is equal to the dimension of W. Why? Because everything in W is an eigenvector with eigenvalue equal to 1.
Mhm.
Does that make sense?
Yeah, thank you.
Okay. Yep. Okay. So so what's the meaning of an orthogonal matrix? Well, the meaning is that it's a n-dimensional rotation. Okay, so why do I say that? Well, let's say I apply some orthogonal matrix. So that means U multiplication by U is a linear transformation from Rn to Rn. What does it do to the dot product between any two vectors? Well, let's just write this in matrix notation. And now the way transposes work, this X transpose U transpose Uy. U transpose U is identity. So this is just X transpose Y. So this is just X dot Y. So U preserves the dot product. And that means it also preserves length and distances. And geometrically, I mean, this is a geometric fact. If you're, I mean, this is what we mean by rotation. It's something that preserves length and distance. This is what we mean by a rotation in high dimensions. Another way to think about it is, you know, the U is just you have the standard basis, which is actually an orthonormal basis. And if you hit this with U, it just gets mapped to some other orthonormal basis. So that's okay. So that's what the meaning of an orthogonal matrix is. Okay, so that's all I want to say about projections and orthogonal matrices. And now I want to move on to something really cool that ties a lot of these things together, which I'm going to call fundamental theorem of linear. It's not really, I mean, it's called this in many textbooks, actually. And so what's the, so what do I want to do here? Well, let's just step back and think about what we've been doing in the course. We've developed many different ways of looking at a matrix. So suppose you have an m by n matrix. Well, okay, the most primitive way of looking at it is it's an array of numbers. Okay, and this is maybe what you thought before coming to this course. Now, in the first, yeah, I'll answer your question after I'm through just explaining this. So in the first few weeks of the course, we developed a somewhat more sophisticated way of thinking about it, which was, well, you should actually think of this as a collection of columns, n columns. And then, you know, we had this important realization that multiplying by a matrix corresponds to taking linear combinations of the columns, right? And, you know, this had all kinds of new, this gave it a, you know, interesting meaning having to do with linear combinations and span and linear independence and all that. Now, more recently, we've been doing something else with the matrix, which is we've been viewing it as a collection of rows. So if it's m by n, it has m rows. Right? And lately, it's been beneficial to view matrix vector multiplication as taking dot products with rows. Right? You can think of it as a Lin combination columns, the multiplication by A, or you can think of it as taking dot products with rows. Why are they transposed? They are transposed because we defined vectors to be column vectors, right? A vector always looks like this. So if you want to put something in rows, you have to, make it look like this. Does that make sense? So I'm thinking of R1 as being a column vector. Let's put it that way. So these R1 to Rm live in Rn actually. Well, because these are columns, C1 through Cn live in Rm. It's not C transpose because C's are already vertical. Does that make sense? Okay. So now I'm going to tell you there's a really deep and important fact, which is that there's an important relation between the rows of a matrix and the columns of a matrix. And this is really the reason why it's so beneficial to write both these in one array, is that you have these two different perspectives that are connected. And what the theorem says is that the dimension of the column space of A is equal to the dimension of the row space of A. Another way of saying that very succinctly is that row rank equals column rank, so rank of A equals rank of A transpose. Okay. So you write these numbers in this array. If you view them as columns, you get one interpretation. If you view them as rows, you get a different interpretation. But now actually, if you look at the subspace generated by the columns and the subspace generated by the rows, they always have the same dimension. Okay. So any questions about the statement? Okay. So let's look at. Yeah, I'm giving the proof. Is your question why is it true or why do we care? By the way, you can speak. I mean, okay, yeah. Okay, so what's the proof? Well, on one hand, we proved a couple of lectures ago that the null space of A is the orthogonal complement of the row space of A. And we did that by using this picture here, right? Okay. And this implied, for example, by applying rank nullity to the projection onto the null space, that the dimension of the null space of A plus the dimension of the row space of A is what? So what's the sum of the dimensions? So remember, these both live in Rn. Yeah, this is for any matrix A. No, nothing special about the matrix. N, right? Yeah. And we proved this in the last lecture, I suppose. Okay. Okay, good. So the dimension of the row space plus the dimension of the null space is n. On the other hand, just by vanilla rank nullity theorem, what is the definition of row space? I'll get to that in a moment. By the vanilla rank nullity theorem, the dimension of the null space of A plus the dimension of the column space of A is also equal to n. Okay, somebody asked what is the row space, so let me just say what the row space is. The row space of A is the span of the row vectors, so R1 through Rm, which is the column space of A transpose. It switches the rows and columns. Does that answer your question? Okay, good. So now we have these two equations, and they're awfully similar, except the only difference is in one of them you have the dimension of the row space, the other one you have the dimension of the column space. So what happens if you subtract these two equations? Well, the ends cancel, the dimension of the nullities cancel. You get that the dimension of the column space of A equals the dimension of the row space of A. Okay, so this fact is often referred to as row rank equals column rank. And what it's telling us is that these, when you put numbers in an array, it wasn't obvious to me. I didn't actually understand this until I was a grad student, so I don't think it's obvious. Why do you think it's obvious, actually? I'm curious. You can talk, it might be easier than typing. Okay, sure. But I mean, for me, this was really the moment when I was like, okay, this is putting things in a matrix is a meaningful activity because there's this connection between the rows and columns. Otherwise, I was always like, well, what's the point of putting numbers in? Okay, that's row rank equals column rank. Actually, something even stronger is true. So here's a theorem. What the theorem says is consider the linear transformation T from the row space. So suppose A is any matrix. And now consider linear transformation T from the row space of A to the column space of A. Okay, by T of X equals AX. This is okay. I'm sorry. So there's a discussion happening which is not correct actually. The discussion happening is why is dimension of null space plus dimension of row space equal to n, and the answer is because row rank equals column rank. That's not what I wanted to say. We're actually going in the opposite direction. So this is true because the dimension of a subspace plus the dimension of its orthogonal complement is always equal to n. That's chapter 6 fact. Okay. I mean, you can prove that by applying rank nullity to the projection onto the orthogonal projection onto W transformation. But this is the reason why it's true. Okay, so let me get back to the theorem. So the theorem says, suppose you have any matrix. Now consider the linear transformation that maps the row space to the column space. So this is a little different because we're used to A mapping Rn to Rm, right? But what I'm describing here is a little different. What I'm saying is that, well, in Rn, so let's say this is Rn, there's a subspace called the row space, and then there's an orthogonal subspace called the null space. Okay. Now, A maps Rn into Rm, and Rm also, I'm going to break into two orthogonal subspaces. The column space of A and its orthogonal complement, whatever that is, right? This is Rm. Okay. Now, the null space, by definition, is all this stuff that just gets mapped to 0. Okay. So what I'm looking at now is I'm defining T to be the restriction of multiplication by A to the part up here. I'm just ignoring the null space, right? I can do that. The row space of A is a vector space. So I can define a linear transformation T only on that subspace. Now the content of the theorem is then T is an isomorphism. Okay. So what's that saying? It's saying that if you look at so A is mapping you from Rn to Rm. T is the restriction of A, the row space. And what the theorem is saying is that, well, this gets mapped onto the column space in a one-to-one and onto manner. For any matrix A. Okay. So people often say this in quotes is matrix maps its row space onto its column space. Okay. So this is even stronger than saying that their dimensions are equal. I mean, well, we know that two vector spaces with the same dimension are isomorphic, but this is actually saying A itself is an isomorphism when you restrict from row onto the row space. So are there any questions about the statement? So let me just draw another cartoon to clarify this. Maybe not make this red. What do you mean by in that order? Oh, row space to column space. Ah, okay. I see. Your question is, what if you went from column space to row space? So you could go from the other way by taking transpose, right? Yeah. So it also works in the other direction, because if you transpose, you're switching the role of row and column space. But this is a different linear transformation, and I should say A transpose is not the same thing as A inverse. Okay. Okay. But yeah, the theorem also holds for A transpose, because after all, the row space of A transpose is the column space of A. Okay, so a cartoon of this is if you think of, if you think of M doesn't have to be equal to N. That's the magic of this, right? If you think of, let's say you're going from Rn to Rm, and they look like this. Well, in here there's the row space, and then there's a null space. What this is saying is that this row space is going to get mapped to some subspace of Rm isomorphically by A. Okay. So when you restrict A to the row space, it doesn't, it becomes an isomorphism. Any questions about the statement? I'll do the proof on the next slide. Okay, so let's do the proof. Okay, so what's the proof? So again, define T. So let A be any matrix. Let T be the linear transformation from the row space to the column space of A by T of x equals AX. Okay. Now we will show this is onto. We'll show T is onto. And we'll get 1-to-1 for free at the end because the dimension is the same. Let's just show it's onto. So what does it mean to show it's onto? Well, I need to show that every vector in the column space comes from some vector in the row space, right? So let B be any vector in the column space of A. And that just means B equals AX for some X. That's just the definition of the column space. So the picture we have here right now is so here you have Rm. Inside Rm, you have column space of A. There's some vector B in here. Yeah, we don't know that yet. Good question. We don't know X is in row of A. That's the whole point. And we know that this came, so this is Rn. We know that this came from somewhere in Rn, but that may not be in the row space, right? So we're not done, right? So this is just true for some X in Rn. So we're not done yet. If this was in the row space, we would be done. But now we're going to do this cool chapter 6 thing, which is, well, we know that the row space and the null space are orthogonal complements. By unique decomposition, we can decompose this X as some X hat, which is in the row space, and some Z, which is in the orthogonal complement, which is the null space. Here I'm using that the row space and null space are orthogonal complements. So what I'm doing here is I'm actually decomposing this X into two vectors. There's some vector X hat that's going to actually end up being in the row space. And there's going to be some orthogonal vector Z, which is going to be in the null space. Okay, but now this is great, right? Now what is A times X? Well, it's A times X hat plus Z, which is A times X hat plus A times Z. But Z is in the null space. So that's just A times X hat, right? Because this is 0. But that's just B. So I'm done, right? I just found a vector. Why the row space and null space orthogonal complements? That was 2 lectures ago. Unfortunately, I can't explain it right now, but that was a couple of lectures ago. So you can just go back and see it. But yeah, the conclusion is that actually every B has is the image of some X hat in the row space. So therefore, T is on. But on the previous slide, yeah, it really is beautiful. On the previous slide, we also proved that row and column space have the same dimension. So then that implies that it has to be 1-to-1, because when you have 2 vector spaces of the same dimension, and you have a 1-to-1, if you're onto linear transformation between them, it's automatically 1-to-1. Yes, so your comment is correct. It's not that X is in the row space of A, but whatever X is, you can find some other X hat so that AX hat is equal to AX and X hat is in the row space. Anyway, the conclusion is this implies T is I. So basically, yeah, the meaning of a matrix is really summarized in this picture. This picture is very important. And if you look at many linear algebra textbooks, this is like printed on the back of it. Any questions about this? Okay. So now, so that concludes what I want to say about chapter 6 for now. And I'll just do a little sort of mini review session just to remind people what the big picture is. Any more questions about this? I'm sorry, this is Rn. Yeah, thank you, thank you.
Sorry, yeah, this might be a stupid question, but could you go back to the last slide?
Yep.
In the cartoon, so we said that this was A is a one onto onto, right?
It's onto the column space of A.
Oh, okay, gotcha.
So the key thing to pay attention to here is, I'll put it in red. I've restricted the domain to the row space, and I've restricted the codomain to the column space. Right? That's the difference. Usually when I have an m by n matrix, I'm going from Rn to Rm, right? I'm not doing that anymore. I'm restricting both the domain and the codomain. And I'm saying that when I do this particular restriction, it becomes an isomorphism. Does that make sense?
Yeah, that makes sense.
Is it important to know what the standard matrix would look like for this transformation? Does it follow pattern? So the question was, okay, the first question is, what's the standard matrix? The answer is, well, you can't really talk about a standard matrix, because to find a matrix for T, you need a basis for its domain, which is a basis for the row space. And the standard vectors may not be in there. So asking about a standard matrix for T actually doesn't make sense, because the domain is not Rn. It's some other vector space. So you need to find a basis for the row space. Does that answer the question? This will not be on the midterm. Why is it 1-to-1? Why is it 1-to-1? Well, it's 1-to-1 because this is this sort of Goldilocks theorem, which is the abstract version of the fact that if you have a square matrix that has a pivot in every row, then it has a pivot in every column. 1-to implies 1-to-1 because it's a square linear transformation. It's from a vector space to another vector space with the same dimension. Okay. Another question, are the null spaces isomorphic? Are the null spaces of A and A transpose isomorphic? Okay, so let me write this question here. Well, think about it. So two vector spaces, of course, to be isomorphic, to have any chance of being isomorphic, they have to have the same dimension, right? What are the dimensions? Well, the dimension of the column space of A plus the dimension of the null space of A is equal to n. That's rank nullity, right? What about the null space of A transpose? Well, the dimension of the column space of A transpose, otherwise known as the row space of A, plus the dimension of the null space of A transpose, that's equal to m, right? Now, these for the row dimension of the column space is equal to the row space, right? So this, so let's say this is equal to R, this term, and this is also equal to R, namely the rank of the matrix. So then this implies that dimension of null of A is equal to n minus R, and dimension of null of A transpose is equal to m minus R. And these are only equal if they're square. Yeah, so your remark is correct. They are isomorphic if the matrix is square, otherwise no. Okay. Any other question? What x would the arrow coming from the intersection between row A and null A be in the picture? Intersection between row A and null A. Oh, you're saying what is this? This is 0. So null A and row A are orthogonal complements of each other. And so this is a general fact. If you have a subspace, the only vector that's in the subspace and its orthogonal complement would be a vector that's orthogonal to itself. The only vector orthogonal to itself is 0. So is that okay? Great. Okay, so this is going to be a very mini review session since I guess we have 15 minutes, but let me just try to give you a high level picture of what we did in chapters 4, 5, and 6. I'll talk about the homework. It'll be new next Friday, but I'll send a detailed announcement. Okay, so what's the review? So, well, what's the story so far? Well, in chapter 4, the key idea was we extended our notion of a vector, right? A vector is anything you can add or scalar multiply. And scalar multiply. So in particular, we extended our notion of a vector. Okay. Yeah. To things like polynomials. Okay, of course, Rn, but also spaces of functions. And even things like spaces of matrices. Okay. Sorry. We have one more question. A maps row space onto its column space, but A is only 1-to-1 if A is squared. No, it's always 1-to-1 and onto. That's the magic of this theorem, right? A can be any rectangular matrix. So this theorem, which is stated here, right? The main statement is this: 1-to-1 and onto. This is always true. Yeah, A is not the standard matrix for T. Another important point: A is not the standard matrix for T. Yeah. Okay, so going back to the review. Yeah, I know. I think it's really quite amazing. We extended our notion of a vector, and the punchline was that everything works as before. So we spent a couple of lectures doing that, but then what we spent a lot of time doing is relating this setup of abstract vector spaces to our original setup of Rn. And so the key ingredient for getting a grip on these spaces, by which I mean, relating to concrete linear algebra, is a basis. So the main thing we discussed was that, well, if you have an abstract vector space V, which just means any vector space. Well, if you have a basis for it, so it's an n-dimensional space, you have a basis of dimension n. Well, then you have this mapping called the coordinate mapping, which was referred to as PB inverse, which maps it into Rn, and this is an isomorphism. Invertible. And what's living down here, so this is concrete, and what's living down here is coordinate vectors. So if what's living up here is vectors, And what's living down there is coordinate vectors of vectors in V. And the point, what I call this, correspondence principle is that everything that's any linear combination that holds downstairs also holds upstairs and vice versa, right? So this was called the. So this was what I, called the correspondence principle. And this is how you turn abstract vectors into concrete vectors, otherwise known as coordinate vectors. And then there was this is how to do vectors, but now what if you have a linear transformation, right? So you have two abstract vectors. Again, the idea is similar. You just do this twice with a pair of bases. So let's say this was the basis B. So now if you have a pair of bases B and C, so I won't write the vectors. So these are input and output bases. Well, then you can do the same thing on both the spaces, right? So you can have this PB inverse going to Rn, and maybe this is Rm. This has m dimensions, PC. And now down here you have the matrix of T, sorry, with respect to these two bases, right, B and C. So here you have T, and the point is this is a matrix. We found a formula for developing this, and again the same thing was true, that any statement about the linear transformation that's true upstairs is true downstairs, and that's encapsulated by this identity. If you look at T of x, if you look at its coordinates in the output basis, this is equal to the matrix with respect to the pair of bases times the coordinate vector in the input basis. This was, these are really the same, it's the same idea. You're turning something abstract into something concrete using these isomorphisms. And the ingredient you need for that is a basis or pair of bases. Okay. Now, in chapter 5, we discussed a few other things like change of coordinates, which is how to change between coordinate vectors in one basis to coordinate vectors in another basis. But let me now say how this connects to chapter 5. So chapter 5 is really motivated by the following question: which, given a linear transformation T from B to V, which choice of input and output bases B gives the simplest matrix? And by now, I really want the same basis for both the input and the output space. Okay, so the reason for that is I actually want to use both the correspondence principle and this second diagram, which is the matrix of a linear transformation. Right? If I want to reason about linear combinations in this space V, I would like to use the same basis for V on both sides. So the answer to this was, okay, the eigenbasis, and the diagram that's sort of given here is, so the idea is choose a basis of vectors on which T acts simply. In other words, of eigenvectors. Or, well, maybe I don't want to put i's actually. So let's put and so the way this connects to chapter 5, okay, we discussed how to find eigenvalues and so on, but the way it really connects to chapter 5 is that to chapter 4 is that let's say you have some abstract linear transformation from V to V, and now let's say you have some basis for this. Let's call that basis S for some basis. Just some arbitrary basis, like maybe some standard type of basis or something like that. And now you have P S inverse, you get to Rn, and now you get some matrix A. But maybe this matrix is, it's not very nice. Maybe it's, maybe this matrix is just some matrix with a lot of entries. Now, the point of chapter 5 was you can further simplify this by switching to, I'm sorry, one of these arrows is going in the wrong direction. By switching to another basis, which is the eigenbasis. So the key is, so now the point of chapter 5 is you find some special basis B consisting of eigenvectors, and now you do another change of basis, change of coordinates really, from S coordinates to B coordinates. So really, the way this is to be interpreted is that this is the P of B from S matrix. And now the punchline is the thing you get down here is great, it's diagonal. Okay, so that's what chapter 5 means and how it connects to chapter 4. So this is a diagonal matrix, which means it consists of n non-interacting one-dimensional, processes. Let's put it in quotes since I didn't define what a process is. And the diagonal entries, okay, maybe I'll just write them here. The diagonal entries are the eigenvalues. Okay. S is just some basis. And this is how we answer the question of what is the best basis. Right? We don't know what it is at the beginning, so we just choose some basis. Now we get the matrix of P in that basis. Right? And then when we diagonalize that matrix, we get a diagonal matrix. And ultimately, by using the eigenvectors, we can get a diagonal matrix for T by composing all of these things. Now, okay, not all matrices are diagonalizable. So the bottom right, it just says processes. Okay, so the reason I said processes is if you keep multiplying the matrix, you can think of it as doing something. Or let's just say non-interacting one-dimensional matrices. One-dimensional matrices are just numbers. And okay, I mean, we discussed how to find solutions of AX equals lambda X. That's okay. Sorry, I'll write better. Sorry about that. And then we also discussed when are matrices diagonalizable, right? So not all matrices are diagonalizable. Some sufficient conditions are you have distinct eigenvalues. You have n distinct eigenvalues. Okay, that's a sufficient condition. A necessary and sufficient condition is that for every, I'll just write it like this. So a matrix is diagonalizable if and only if for every eigenvalue lambda, the geometric multiplicity is equal to the algebraic multiplicity. And the way, okay, the algebraic multiplicity was the number of times it appears as a root of the characteristic equation. And this is where chapter 3 came in, right? That's actually why we did chapter 3, just so we could solve that characteristic equation. Okay. So that's how chapter 5 relates to chapter 4. And chapter 3, there's one important caveat, which is, okay, not all matrices are diagonalizable. Sometimes you need complex numbers to even get n eigenvalues. And complex eigenvalues correspond to two-dimensional rotations. Okay, so that's all I want to say about chapter 5, and I'm really out of time, so let me just very quickly say about chapter 6. So chapter 6. Chapter 6, if there's a complex eigenvalue, the matrix is diagonalizable if you allow complex eigenvectors and eigenvalues. Okay, so so the two-dimensional rotations of real vectors. So what I mean by corresponds to two-dimensional rotations is, I mean that when you have a complex eigenvalue, there is a two-dimensional subspace in which the matrix is performing a rotation. That's one of the theorems that's stated in the book. Okay, so let me actually answer this question. So maybe before getting to chapter 6. So the question is, if complex eigenvalue is the matrix not diagonalizable? So the answer, well, depends on what you mean by diagonalizable. So, for example, our favorite matrix, right? We looked at our favorite matrix with complex eigenvalues, right? Has eigenvalues plus or minus I. Right? This is not diagonalizable over R, which means it's not equal to PDP inverse for every real P and D. However, it is diagonalizable over C. So there's some matrix P I think it's this. Okay, so it is diagonalizable over C. So over R means with real matrices, over C means with complex matrices. So the answer to your question is, it depends on what kind of diagonalizability you're looking for. So often, algebraically speaking, this is good enough. And there are many, that's the reason for introducing complex numbers. There are many matrices that can be diagonalized if you use complex numbers, not without. Does that answer the question?
Just a follow-up. So for the midterm, is it going to be specified if we are doing it in R or in C?
Yes. This will be made completely clear over the midterm. And really, I'm not going to ask any tricky questions about this right now, because we're actually going to be looking at it much more in the differential equation section of the course. But yeah, it will be specified if it's asked. Is the midterm MC? No, sorry. The midterm is just going to be like a regular midterm now. Okay. So okay, I guess I'm really over time. Let me just say a tiny bit about chapter 6. The key new idea is orthogonality. And this means, I mean, some consequences are that some bases are better than others. In particular, orthonormal ones. right? That's previously we just talked about all bases being equally useful. Orthonormal bases are better because they allow you to decompose vectors into non-interacting components. Okay, so in some sense, this orthonormal bases are generalization of the standard basis. The standard basis is great because, you know, in some sense, the coordinates don't interact. You change one of the coordinates, it doesn't change any of the other ones. If you, okay, so
Wait, what do you mean by some bases are better than others?
well, I mean, orthonormal bases are better than a general basis. So, okay, why is it better? Well, for example, you can find coefficients easily using dot products, right? You can't do that for general basis. You need to do row reduction. Does that make sense? Like finding coefficients with respect to an orthonormal basis is much better than a general basis, much easier.
Okay, I see it now. Thank you.
And then maybe the key idea was that there's this relationship between optimization and orthogonality, right? So so you had these two problems of decomposition and you had this other problem of, you know, find the x hat in some subspace closest to x. And both of these were solved by the same device, which was the projection of W onto X. Okay. So this is an optimization problem. And so the point is that this optimization problem was solved by an algebraic. It had a solution that could be characterized algebraically in terms of the decomposition theorem. So decomposition and I guess this best approximation theorem turned out to be the same thing. And this is really the main theme. Okay, sorry, this last slide is shabby, but I guess I'm out of time. But if I had to say that this was really one of the main themes of chapter 6. And then finally, we used orthogonality and this important fact that the orthogonal complement of the row space is the null space to prove the fundamental theorem of linear algebra. And row rank equals column rank. Okay, well, sorry to go over. That's it. Anyway, good luck on the midterm, and I'll have extra office hours on Monday.